Hello. I'd like to take a few minutes and do some highlights of Chapter 3 of Healey, Measures of Central Tendency. We're talking about a distribution, and in statistics we've talked about variation. We are talking about variables, dependent variables, independent variables, how age is a variable. We don't all have the same age. Income is a variable. Gender is a variable. We're not all the same gender. One way of thinking about variation in terms of the mathematical properties of it is as a distribution, so that we take variation and frame it, reframe it, or recast it in terms of numbers. Like, for example, we'd know that age is variable, so what we'd want to do is look at the distribution of age. What's the lowest value? What's the highest value? What are the values in between? That's a continuous variable. We'll speak to that for a few minutes, and we'll look at categorical. We have three measures of central tendency that are important to us: the mean, the median, and the mode, and we'll take them one at a time. But let me step back for a moment and talk about what we're going to do next week, and that's Chapter 4. A good way to think about the measures of central tendency of Chapter 3 is that what we were doing there is we're summarizing into a single value the extent of the distribution into the center, the mean or the median. We're collapsing it. It is like we might think of as a teeter-totter, where the center of the distribution is the fulcrum that the teeter-totter sits on. And so we're looking for that middle value that provides kind of a balance to the distribution. Now, next week we'll do measures of dispersion. As you can imagine, as we collapse it down to the center value, which we'll talk about here in a minute, we lose information. Once we collapse it down into, in this case, the mean of 5.8, and we say the mean of this distribution is 5.8, that's cool. We know that. But we don't know if that's what we're reporting. It's just that. What are the other values behind that led to that 5.8 mean? We're losing information when we summarize distributions into a single value. Summarizing them in a single value is very cool. We think about in baseball averages. Somebody who has a baseball average of 400, suppose if somebody has a 300, we'd say the 400 has a better average. This time now in this part of the world, we're concerned about rainfall averages. Rainfall average is lower than it was before. So we think about averages. And so this is about somebody in the background when they're doing the rainfall average, right? Say for 2013, has looked at the rainfall by day, summed up the rainfalls for each day. Each day is an X in the distribution. Summed it all up, the sum of Xi, divided by the number of days, 365, and come up with an average rainfall for a day. Or they may have done it over the course of a number of years to get the average rainfall. So we know about averages. That collapses a wide distribution into a single value and allows us to do some comparison. Rainfall last year average, rainfall this year average, baseball average this person, baseball average that person, average age in this class, average age in that class. If we know something about the average ages, we can say, well, this person, this group is probably a little lower than that group. We use these a lot. All right, so when we're thinking about the variability, we'll think about it in terms of distribution because that's the numerical expression, shall we say, of the variance. Let's look at the mean first. Now I've got a small distribution here of 5 values, x1, x2, x3, x4, x5, 3, 5, 6, 7, and 8. Now we know out there in the real world, we're talking about distributions much larger than this. If you're working in a community-based organization, you might have 150 clients or 300, so you'd have 300 values. Years ago when I did my dissertation, I was working off 40,000 birth and death certificates. So I would have had 40,000 of these. The U.S. Census comes in here and say in San Antonio and wants to calculate out the average age of the city. They got to ask all million or 2 million of us what our ages are, sum all that up and divide by 1 or 2 million, whatever there is of us, to get the average age. That is a huge distribution, millions. Go around the room on a chalkboard many times. So what we're doing, we're using a small distribution of 5 values to illustrate the principle of this. And I'm not defining this as anything other than a distribution. It's not age, not weather, not nothing. Okay, so let's look at it from the standpoint of the mean. So you'll see in the text that the way to calculate the mean is, which is known as the x bar. You've got the sum of xi over n. So here are the x. Xi means all the x's in the distribution. So you sum up 3 plus 5 plus 6 plus 7 plus 8, and you get 29 if my math is correct. There are 5 values in the distribution. Divide by n, and we get a 5.8 is the mean. Pretty close to the center, right in here somewhere. All right. And so here's another, it's something about the characteristic of the mean that's important, what I'm trying to illustrate here. Here's 5 values in a distribution again, 3, 5, 6, 7, and 20. Still the same number of in the distribution of 5, but here we have what we would call an outlier, a value that's very much different than the values, shall we say, in the normal values distribution. This value out here, when we add this up with the 20, we get xi, sum of xi over n, we get a 41 over 5, we get a mean of 8.2. The mean is off here to the right. So what you see where here the values are somewhat similar, 3, 5, 6, 7, 8, not that much variation between any two values side by side. Then here, when you put that 20 in there, it pulls it to the right. The mean moves in relation to the values in the distribution. If we had a low value here, let's say, if we left this here and we change this to a 0, it would pull the mean to the left because the number up here would be smaller. And so what we would divide 5 into a smaller value would get us a mean over this way. So here, then, you can see that the mean is influenced by outliers either on the left hand of the distribution or the right hand distribution. It's a very important value. Average this, average that. We use it frequently for comparing things, as in baseball averages, batting averages. Let's say use that as an illustration. Even if you don't know baseball, you understand rainfall averages. We understand that one for sure. So when we look at the same distribution from the standpoint of the median, a significant difference between the two. The median is sort of the geographic center of a distribution, and it's uninfluenced by values at the outlying ends of either the left or the right of the distribution. You'll notice here, for example, even though the median is the center of the distribution. So let's go through this. This is an odd number, 1, 2, 3, 4, 5. This is all laid out in your textbook. Odd distribution. So we would add up the numbers in the distribution, which is 5, plus 1 is 6, divide by 2, and 5 plus 1 is 6, divided by 2 is 3. Now 3 here is not the median, it is the position in the distribution where the median lies. So then we would say, if this is the case here, this is odd, 1, 2, 3, that's the median. Median is 6. Now it's easy to eyeball, right? It's only got 5 here. Obviously that's the center of the distribution, the geographic center. But if you're out there working in a community-based organization, you've got 300 clients, it ain't gonna be so easy to see. So again, we're using a small distribution like this of 5 values, to illustrate a principle. Now, that's when it's odd. When the distribution is even, such as this one, 1, 2, 3, 4, 5, and 6, the median then is, where are we here? Is 6, here it is, the number in the distribution divided by 2, and then plus 1, and then divide that by 2. And basically that's kind of muddled, I suppose, but here's what it adds up to. So we've got 6 in the distribution, divide by 2, that's 3. That's position 1, 1, 2, 3. And then plus 1 makes position 4. So then as we come over here, you can see 6 plus 7 is 13. We divide by 2, and we get a median in this one of 6.5. So here's the median in this distribution. And in an even, what it does, it takes the two center values in the very central geographic center of the distribution, adds them up and divides by 2. Now again, if this were a distribution of several hundred, you wouldn't be able to see it, where you can see it here. Again, we're talking about illustrating a principle on a distribution of only 5 or 6 values. So here you can see that on this one, the median is very close. The median and the mean are very similar. But there is a case where the mean and the median are in very different places, and I want to look at those shapes here in a second. But I want to point out one more thing, or two more things. Well, before we go over here, here's mode is the other one. Mode, I think, would be best said is a best central tendency descriptor of categorical variables. And by that I mean variables that are defined by categories like gender, male, female, ordinal, which are, say, attitudinal, very happy, happy, not so happy. The mode is the category that has the most. Doesn't have to be 50% or more, but the one that has the most. It could be 32%, 32%, and 40-some-odd%, but not 50% for the third category. So the mode is the category that has the most. Now in gender, unless it's a 50-50, in which case there wouldn't be a mode. If it's 60% women in class and 40% men, then we'd say the mode is female. In a numerical distribution of continuous, modes are not so helpful, shall we say. I mean, this is okay. Here we can see the mode is 2 5s. So the mode would be any value that has 2 or more of the same value. So 5 is a mode in this small distribution. If you have a distribution of 1,000, you might have several modes. So modes don't really work so well, in my view, with continuous variables, but they're very helpful, shall we say, very helpful in identifying categories in a categorical variable that are modal, the ones that have the most. Not necessarily 50% or more, but the ones that have the most. So these are the 3 measures of central tendency. Always with the image of collapsing the distribution down to a single value in the center of it, so that in continuous variables you're imagining a teeter-totter. So if you get that median in the geographic center, the teeter-totter sort of balances out there like this. And that's what you're after with the median. Now, realizing that the median, no matter what happens, like if you see here when we had a large value, the mean went to the right. The median stayed the same. The median is 6 here, and the median is 6 here. When we did the large outlying value, the mean shifted to the right, but the median remained the same. It's always good when you're doing reports and when you're looking for reports that you look for the median and meaning in a report, and mean when you're looking at reports, and when you report out both the median and the mean. If you had nothing about the distribution, nothing, but you knew something about it, that you had the median and the mean, you would know something about the shape of the distribution, which we're going to talk about in a minute. The closer those 2 values are together, the more normal the distribution. I'll draw that out here in a second. The farther away they are from one another, the more skewed is the word that we'll use, is the distribution. We'll talk about that here in a second. One other thing before I erase this and put a few shapes up on the board here, is one of the things we might want to know, which is really kind of the subject of next week. Here we're collapsing to the center, right? All these values. But there's dispersion or variance here. The variance between 6 and 7, 6 and 8, 8 and 7, 8 and 5, 3 and 6, 5 and 7, etc., etc., etc. Particularly we're interested in variation around the mean. How much variation is there around the mean? Now, one of the things that we can see just looking at this distribution is if we were to decide that we wanted to subtract the mean from all the other values, we're going to get something interesting that will happen that will carry through the other things that we do. If we subtract 6 from 7 or 6 from 8, we're going to get plus values. If we subtract 6 from 5 or 6 from 3, we're going to get minus values. So in a little bit in next week, but in particularly chapter 5, we're going to be talking about things to the right of the mean as positive, things to the left of the mean as negative. This is the positive side of the distribution. This is the negative side of the distribution. And you'll see it in a minute when we talk about skewed. Now, you might think one of the ways that we could understand the variation around here is simply to subtract the mean from all these values. Well, we have to think about that, whether that's really what we want to do. Here, for example, is that distribution vertically, 3, 5, 6, 7, and 8. There's the mean, 5.8. I'm subtracting 5.8 from 3, 5.8 from 5, 5.8 from 6, from 7, and from 8, and this is the value. All right, so if I sum up these two, I get a minus 3.6, right? If I sum up these three, I get a plus 3.6. If I add minus 3.6 plus 3.6, I get what? A big fat 0. So it's not going to be the case that we could take the easy route and subtract the mean from each of these values, because if we do that, we're going to come up with a 0. What you'll see that we do, and it talks about in the text, and this will become very important to us next week in chapter 4, we square these values. And when we square these values, of course, it takes out the minus and plus signs. It turns them all into plus. And then when we sum up the squared values, we get the total. We get what we will call the total variation or variance. So it's an important thing to keep in mind that in these distributions like this, it's not a simple matter of subtracting the x's or the mean from the x's, because it'll sum up to a 0. An important principle to keep in mind, and you'll see as we go into next week and on into the semester, we're going to be talking about something we call least squares, and it comes from squaring these values. If we square these values around the mean, we get the least squares, and we'll talk more about that next week because there's some illustrations that will be important. Okay, so I'm going to erase this, and it's a bit cluttered, but I thought it'd be better to set it up and save some time than to not do that, and then while you twiddle your thumbs, I draw things out on the board. Well, you can twiddle your thumbs for a moment because I got to erase this. And now I'm going to do I'm going to do 3 drawings. I'm going to do one that looks like this. Whoa, that's pretty good. And then I'm going to do one that looks like this. And then I'm going to do one that looks like this. All right? All right, now, where we've got the mean and the median, let's say where the mean more or less equals the median, we've got a normal curve. It's bell-shaped. Here they both are right here. Here's low value, here's high value. You'll see this in the chapter, and we're going to talk a lot about this over the course of the semester. And here then, everything to the right, this is the means, everything over here, this is the plus side of the curve, and here's the minus. We just saw if we subtracted all the x's over here, then all the x's over here are smaller. We would get negative on this side. Let me point something out to you real quick. All right, so we've got 3, 5, 6, 7, 8. Let me show you how. I want to keep in mind where these shapes come from. If we had 2 5s like this, so that we had a histogram that looks like this. So that the value, there's one value of 3, one value of 8, 2 values of 5, 2 of 7, 3 of 6. These are bar charts, but because the walls are contiguous, if you remember from chapter 2, that makes them a histogram. Histograms indicate a continuous variable. Bar charts with space, remember, are the difference between are about categorical variables where there's no scale between the values of the categories, or between the categories, I should say. So then, when you get these in, you do a dot to dot, just like in early days of our education. Some of that stuff we did was when we were much younger, in that sense. So what we do is we do a dot to dot, like that, and voila, kind of awkwardly drawn, is a normal curve. So when you see these kinds of polygons, always imagine in the background there is a histogram, and that these are the expression of a dot to dot across the top of the bars of a histogram. Always keep that in mind. There are data back in behind here that give the shape, just like you see here. All right, so that's where the median is, and the mean are roughly the same. Now these two are called skewed distributions because they're not normal. Here, this is the tail and the right tail, the positive side, the negative side, the positive tail and negative tail. This little value out here, if we subtracted 6, we would get minus 3. It's out here on the negative side. If we subtracted 6 from 8, we'd get a plus value. It's out here on the high side. 8's out here on the high side. All right, it's positive and negative.
Well, here you see when the median, let me put it this way, when the mean is larger than the median, you get a positive skew. Here's the median, and say over here is the mean. Like in that case we added 20. We substitute 8 and put 20. It pulled the mean to the right. That was a positive skew. It's positive because values to the right of the mean, or the right of the mean, which is in the center of the distribution, are positive. So it's a positive skew. It's got a tail. Tail is out to the right. If we've got a case where the median is smaller than the mean, right? Did I get that? No. Where the mean is smaller than the median, let's do it that way. If the mean is smaller than the median, we got the mean out here, and then the median over here, then it's pulled to, it's a negative skew, pulled to the tail on the left-hand side, which is the negative tail. So this is a negative skew, that's a positive skew. Now you may say, what's the, well, there is a point actually. We'll see as we get into 5 and some others. The assumption is, and you'll see how this works, the larger the sample size when we're doing inferential statistics, the more normal the curve is. So we're assuming normal curve, and if we're estimating what's up in the parameter is a normal curve, because up in the parameter and the population we got 1 million, more it's normal. We'll go through that logic when we get to Chi. When we've in our sample, if we got something that's skewed, we have to think about want to knock off that outlier to more normal in its distribution or to get a better estimate of what population parameter is. So we've a lot to think about. The way that we get that image in to think about it is a normal curve where the mean are roughly the same, and a skew to the right and to the left, positive skew and a negative skew, things that are important to us over the course of the remainder of the semester. Okay, so tendency, chapter 3. Next week, collapsing to the center. Next week, chapter 4, measures of dispersion. What is the variation and dispersion of rain? Now that we've collapsed to the center and lost the into the center, we get to 5.8. We don't need in 3 and 5 to see that single value. We've lost information. When we measures of dispersion, we go back to distribution, look at the variation around the mean, cover all the dispersion between x's on either side of the mean. So it's important, point, counterpoint, complementary, collapsing to the center, expanding out in the dispersion. Collapsing to the center, expanding out dispersion. And like in the mean, as representative value of the distribution value, we will have something called the standard deviation dispersion. It will be very handy for us to capture the amount of dispersion. In other words, here if we've got a mid is larger than the other, say age is old, age is 52, age that's a group that's 52. When we have a deviation, means smaller deviation means a dispersion of this week. So we'll close the and